All right, let's get things started. Hello, everyone. How's it going? Hope you're all good. Yes, last lecture of the semester for new material. We are going to be talking about partial derivatives today. It's going to be cool. It's going to be fun. Of course, you have to remember regular derivatives, or else you're. It's going to be interesting. It's going to be interesting. But hopefully you guys can actually catch on to what we're saying. So let's PTSD. No, there'll be much more to pick up on in 213, so don't miss it too much. You'll do a lot more of this stuff in the next class. Don't worry. So cutting off the video, let's get down to business. Some people have to go a little early, so let's try to get through the meat and potatoes before that happens. So as I mentioned, but I'd have to mention it again, final date, finally set in stone, Thursday, May 21st, 3:30 to 5:45 p.m. It will be on Blackboard, and we will do a trial run of Blackboard later today. So hopefully you guys got logged into Blackboard and you know how to get in. We're going to do something together today just to kind of feel out what the final would be like. Today is the extra class, which is Friday. So obviously, if you're here, you already know that. This is what we covered last time. We started talking about limits and continuity. We looked at how to show limits do not exist, how to show that they exist. And so now we're moving on to the last topic, partial derivatives. Dum, dum, dum. Okay, so partial derivatives. Obviously, the derivative is a very important guy in calculus. In Calculus 1, we spent more than half of Calculus 1 on the derivative. It was the solution to the rate problem. It was our way to try to figure out how fast something is changing, and it turns out that it's useful in many other contexts. It's also can be thought of in some sense, the inverse operation of integration, which is the solution to the area problem, and it was really cool. However, the derivative was defined in terms of a limit, and as you realize, when we go from a 2D world to a 3D world, the idea of limits really kind of changed. A limit now was a lot more things had to go right. Infinitely many more things had to go right. Now we don't only have to look at 2 dimensions, we have to look at an infinite number of dimensions, and just getting a limit to work is a lot harder. This will, of course, have consequences for the derivative. And the consequences only compound on each other the higher in dimension we go. Eventually, you're not going to see this in 213 either, but eventually derivative is going to morph into this sort of matrix function where there are partial derivatives into the components. This is called the Jacobian matrix, and that would be called the total derivative. That's the derivative in its full glory. We are not going to talk about that, and you probably won't talk about it in 213 either, but for those of you who are curious, here's a link that you can check out to talk about the total derivative and what it would look like. You'll need some linear algebra background though, but we're not going to discuss it. What we are going to discuss is one point of view of the derivative that is, in its own right, very useful. Even to build up to what a real derivative is, we need to know about this kind of derivative, which is called a partial derivative. So for lack of a better way to define it, the better way to define it, of course, is by the limit definition. But essentially what this is when we're taking derivatives with respect to one variable at a time. So you're doing a partial derivative. You have several variables, but you want to differentiate with respect to one variable at a time. And essentially what this boils down to is you go to the limit definition of the derivative. Of course, it's a 2-variable function, but you let one variable change at a time. So you have the x plus h, but the y stays the same. Or you can have the y plus h, but the x stays the same. So this is a new idea for a derivative. So there are several variables moving in our function, but we just decide, you know what? Let one variable just stay as is, and we will actually move one of the other ones according to the limit definition of the derivative. This results in what's called a partial derivative, okay? And it, of course, leads to a new notation. So regular derivatives, so, and the regular derivatives are called ordinary derivatives. So for example, this here, this is called a ordinary derivative. And we use this notation here, d dx. So this is with respect to x. But now we're going to talk about what's called a partial derivative. And we use a different notation. We curl the d, so it looks like that. So there were times in Calc 1 when people would be writing the derivative and they'd write the derivative with this weird d that's kind of too curly, and I will actually write in, okay, no, you need to write the d a little bit more straight here, a little bit more proper, because there is going to come a point where the d is going to change, and that actually brings with it a different interpretation, okay? So, so this is, we have a few people stepping in now with respect to x. And this is called a partial derivative with respect to x, okay? And here are the notations. So this curly d is, that you see right here, this is the Leibniz notation. And it turns out the closest thing to Newton's notation is a subscript notation, right? So there's no prime notation anymore. The prime is just not detailed enough. It's missing too much information, okay? So we can have the Leibniz notation or the subscript notation, and you can use any one of these that you want, just don't mix the notations, right? So a lot of times when I'm writing things down by hand, I'll use the subscript notation just because it's easier to write down, not because it's any more correct than the other one. But it can be, the Leibniz notation is useful in some situations, like if you're doing the, when it comes to writing things down quickly, the subscript notation is superior. However, there are problem types where you really want to pay attention to what's going on, and the Leibniz notation will probably be what you will use. Anyway, where was I? So that's the new notation. And as I mentioned, this is the definition. I would say you should have to memorize the definition. However, you're not really going to use the definition to actually compute anything. So I wouldn't worry about that. So that's what a partial derivative is. Basically taking the derivative with respect to one variable at a time, pretending that the other variables are fixed. And I'll talk a little bit more about that as we move on. This is the definition. You should know them. It's very similar to the limit definition of the ordinary derivative, except you, of course, you have several variables, but only one of them get a plus h. Now, geometrically, what's happening when we take a partial derivative? So here we have some function here. So we can talk about a partial derivative as kind of being the derivative in the x direction. So we pick a point in our function, and we just want to find, well, if we can imagine just a curve being traced out that's parallel to the x-axis, and we find a derivative in that direction, that would be the partial derivative with respect to y. Then the other way would be the partial derivative with respect to x. So even though it's in 3 dimensions, there's an infinite number of directions you can move in, we're moving in the x and y directions specifically. And this is just this is what's called a partial derivative. So to visualize it a little bit more, here's what actually happening. So you can imagine that you're taking a plane, let's say, so this is a plane of, say, y equals k. Slicing it through your surface, you will create a curve, right? You'll create like this curve here, the curve of intersection. Now, you look at that curve of intersection and pretty much be able to draw a tangent line to it. The slope of that tangent line is going to be the partial derivative with respect to y. Or you can do it the other way, slice through, or with respect to x, slice through with a plane of that sort and find the curve of intersection, which is going to be the curve here, that kind of brings things back down to your single variable calculus world, because now you can just look at it as a curve, and then you can find the slope of the tangent line to that curve in that direction. Okay, and so that's geometrically what a partial derivative is. It's kind of like you're finding the derivative of a trace. Yeah. So whenever you fix the y to be a constant and find the derivative of that trace curve, the slope of the tangent line to that trace curve, yes, that's the derivative with the partial derivative with respect to x, and the other one is the other way. Yeah, tangent, but of course you can do this for every point, right? So you can find the derivative at a specific point, right? But the function that can define the derivative at along the curve, that is what we call the partial derivative. Okay, so this is just another point of view. This is actually from your textbook, and it has a little bit more things there. Although geometrically, again, that's something that you don't really need to know how it goes, but that's just showing you what it means. So that kind of goes from the 3-dimensional case to the 2-dimensional case, which you're familiar with. That's kind of what you're interpreting. So the partial derivatives are just the derivative in particular directions. You can imagine that these are just derivatives based on a bunch of trace curves. But of course, it is a function. So no matter whether you slice the trace curve here, or you slice it here, or you slice it here, you're describing a function that can find the slopes of tangent lines to this trace curve at any given point. This is the partial derivative. Okay, so now, what do we actually need to know? And what does this mean for us computationally? I'm glad you asked. Okay, so essentially what this means is you kind of take the philosophical point of view. If you want to find the partial derivative with respect to x, which means x is your variable, x is the guy that's moving, you just pretend that all other variables are not moving. You pretend all other variables are constants. And so you just go through and you find the derivative kind of like you normally would. However, you would just pretend that every variable except the one that you're currently working with, the one that you currently want to take the derivative with respect to, every other variable, as far as you're concerned, is a number. They might as well all be 5 or 7 or pi or whatever. They're just numbers, okay? So let's actually try, just jump right into an example, because I don't think there's much more to explain than that. If you see a few examples, hopefully you'll actually catch on to it. So here we have an example right here. So we have this function. Okay, so that function. Find all partial derivatives of f. Okay, so f of xy is a 2-variable function. This means it has 2 kinds of partial derivatives. Namely, partial with respect to x and partial with respect to y. Okay, now let's look at one of them. Let's talk about the partial with respect to x. Okay, so here, here's my f of x. Let's find the partial with respect to x. So I can do this, partial of f with respect to x, or I can write f sub x. Now, what that means is whenever you see that, pretend all variables besides x are constants, right? Now, other than that, you go through and you take the derivative kind of how you always do. So you have to obey all the derivative rules. So chain rule, still a thing, product rule, quotient rule, still a thing. All your derivative rules would look the same. So for example, you go through X is your only variable now. So how do you differentiate 3x squared? Well, 6x using the power rule. Now, you have minus 2x cubed y. How do you differentiate that? Well, the y is a constant and the 2 is a constant. We know how to differentiate constants. You leave the constants alone. Then you differentiate the function, which is 3x squared. Plus, move on to the third one. 3xy cubed. Again, the 3y cubed is a constant. You leave it alone. Then you differentiate the x, which is a 1. Minus, so what would be the derivative of 2y to the fourth? 0, right, because y is a constant as far as x is concerned. So this would mean that your partial derivative with respect to x is 6x minus 6x squared y plus 3y cubed. And that's basically it. If I were to find the partial derivative with respect to y, the 3x squared is a constant, so his derivative is 0. Minus 2x cubed y, that is just a constant times y. We know that the derivative is just a constant. Plus, we have 3xy cubed. Of course, 3x is a constant, then I differentiate the y cubed. Minus 2y to the fourth, that becomes 8y cubed. So this means that my partial with respect to y, minus 2x cubed plus 9xy squared minus 8y cubed. I wouldn't say partial derivatives are easier than regular derivatives. Partial derivatives, computationally speaking, are exactly the same as regular derivatives. The only thing is you just have tunnel vision while you're doing it. All variables except the one you're currently focusing on, they're constants. It's extremely easy to follow because you already know about derivatives very well. So you guys have been doing derivatives for at minimum like 8 months at this point. It's something that you should be very good at. But the rules are exactly the same that you learn for ordinary derivatives. So it's not like one is easier, one is harder. There are situations in which the multivariable case is harder, depending on what you want to actually do. But that's neither here or there. Computationally speaking, the kind of algebra manipulations you'll be making would be the same as before, the same as in single variable calculus. Okay, so everyone seems to be catching on to it. That's good. Let's go. Right, so as I mentioned this already, all your old derivative rules apply. So let's do another one. So here I have z is equal to y e to the xy plus sine x over y. Now I want you to find the partial derivative of z with respect to x and find the partial derivative of z with respect to y. Okay, all right. Ash, Mr. It's extremely easy. How about you do this one for us? And of course, David can take the second one because you guys are out here like talking trash and partial derivatives. I gotta call them out. They were talking trash. Yes, David, do partial with respect to. Okay, so Ash claims it's y e to the xy plus cosine of x over y. No, that is incorrect.
I have a question.
Yes.
So when you're doing the partial fraction and you're trying to find the first variable, like z of x, do you like completely ignore the y variables?
No, you don't completely ignore them. You consider them constants. That's different from completely ignoring them. So you don't ignore them, you just pretend they're constants. So you would treat them how you would treat any constant. So let's actually talk about how would we treat a constant. Suppose we had something like, I asked you, now think back in Calc 1, right? The derivative of, say, e to the 5x, right? How would you differentiate that?
It would be 5e to the 5th x.
Right, because there's a rule that says the derivative of e to the u is u prime e to the u, right? That rule still works, okay? So when you want to take the partial with respect to x of e to the xy, remember, your y is a constant. The y is like the 5. It would play the same role that the 5 would play. So you literally take the derivative of x times y. Well, that's just going to be y, right? And so the partial with respect to x of e to the xy is actually y e to the xy. And so the first term, because there's a y there already, this becomes a y squared. Now, of course, for the second one, I think you're fine. Cosine of x over y. Now, remember, the y is just a constant. This is like differentiating x over 2. The answer would be a half, right? It would be just 1 over the constant. And so that is the partial with respect to y. Yeah, you got it. All right, David, take it away. So e to the xy plus x e to the xy. No, you're missing something. So yes, of course you need a product rule, right? So we need the product rule for the first term. So you would differentiate the y, leave the e to the xy. Well, that just leaves you with e to the xy. Plus, you leave the y, differentiate the e to the xy with respect to y. That gives you x e to the xy, right? So you're missing the original y. Right? So this is a product rule for the first term. Okay, some of us are a little bit skittish. Again, whenever I do anything with partial derivatives and you're confused about it, it means you're confused about something with regular derivatives and you're just not seeing it. So again, imagine if it was a constant. Imagine that my x is a constant. Suppose I had, say, the derivative of x, or maybe I should do y's just to make it a little bit more clear. Suppose I wanted the derivative with respect to y of y e to the 5y, right? So pretend the x was a 5. What would you have done? Well, you differentiate the y, you leave the e to the 5y, plus you leave the y and differentiate the e to the 5y, which is 5e to the 5y. Right? Now compare that, what I just wrote, to what I wrote here. You differentiate the y, you leave the exponential. Plus, now you leave the y, differentiate the exponential. How do you differentiate the exponential? Well, it's the derivative of the power times the original function. What is the derivative of the power? Well, the derivative of xy with respect to y is x. Constant times a variable, the derivative is just a constant, right? Derivative of 5x is 5. Derivative of 7x is 7. Derivative of pi x is pi, right? These are all things that we know from ordinary derivatives. You're doing the same thing here. Now, plus, we're going to do the chain rule. So the derivative of the outer function is cosine. Leave the inner function alone. Now we have to multiply by the derivative of the inner function. Now the inner function, this is really xy to the minus 1. How would you differentiate that? Well, with the power rule, of course. The x is just a constant. Leave it alone. And then differentiate the y. Right? The derivative of sine is positive cosine. You're thinking of the integral. The integral of sine is negative cosine. Right? So then we have this. Okay. And so here in these blues, I'm just comparing it to, you know, a time long past. Okay. And so now we can clean that up a bit. So this is going to be e to the xy plus xy e to the xy minus x cosine x over y squared. This is the derivative. Okay, how are we? Anyone still lost? Did we kind of get what's happening here?
Yeah, I got it. Thanks.
Okay, cool. So it's just, you kind of need the tunnel vision, which is something you have to work on. It's just like you have to look at a letter, but just pretend it's a number. And you do that for all letters except one of them. You kind of, that's kind of how it is, right? So you're doing the same old rules. You're just thinking of everyone as a constant except one guy at a time. And so however you would deal with a constant in some situation is how you have to deal with all other variables other than the one you're currently taking the derivative with respect to. And I think that's the only, okay, here's I'll do that after. Let's move it over here. Here's another one. How do you differentiate this one? Implicit differentiation is going to come back. And I might even show you guys something nicer. So you might remember implicit differentiation from before. I'm going to show you something that's going to be cool. And in some ways, it's going to make your life a lot easier. Right, quotient rule. So again, remember, everything still applies. So you guys remember what the quotient rule said? So this is Calc 1.
Is it
If
like
we want a d dx of f over g, this was low d high minus high d low over low square. Yeah. F prime times g minus f times g prime over g squared. Right. So we're going to do the same thing. We're thinking of the cosine x as the f. We're thinking of the x plus y squared as the g. And so now we're going to find the partial with respect to x. Now that means think of all y's as constants. Okay, so here's cosine x, and this is x plus y squared, but hey, that y is a constant as far as we're concerned. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom, which is going to be what? Right, all over the bottom squared, x plus y squared. So that's going to be minus x plus y squared sine x and we can cancel the x plus y squares here, right? No. Okay, good. Because I would have like thrown my tablet at one of you if you said yeah. Okay, let's cancel and cross sums. Can't do that. Oh, but I factored out the negative outside. So that's why I put a plus here.
We learned that the first day.
Yes, we did. So there was a negative here and a negative here. I didn't just want to write two negatives in the top, so I factored it off in front of the fraction. So it's a negative times that. Yes, this is a combo of two classes. So both the GH section and people from the GH section and the RH section are here. All right, let's look at implicit differentiation. Do you guys remember how that worked from single variable calculus? Hopefully you do. Pretty much now, you don't think of the other variable as a constant necessarily. You think of the other variable as a function of the first variable, right? So let's again compare to the Calc one, just so that we're kind of on the same page here. Suppose I said find dy dx if we know that x squared y plus 2x equals 5y plus 7. Okay, what did we do? Well, we thought of the y here. Think of y as a function of x. Okay, and so what that means is we had to apply the chain rule. Let's make that y cubed. We had to apply the chain rule whenever we're differentiating y, because it's not just a y cubed. We're thinking of this as some function of x cubed. So it's an inside function. Everywhere I see a y, I think of it as an inside function. So what we do is we go through, do the product rule, differentiate the x, leave the y term, plus leave the x, differentiate the y term. Whenever we did that, we multiplied by dy dx, right? Because now that chain rule takes effect. Plus differentiate x, 2x, this we differentiate 5y dy dx. And of course 7 is 0. And then now you solve for dy dx. Okay, so let's actually work through this, because I actually want to show you guys a cool thing that we can talk about. Even though technically it's not in our syllabus, it's really quick to actually show you right away. So what would you do here? Well, you would pretty much keep everyone with the dy dx. This is the guy that you want to solve for. So you bring all the dy dx's on one side. So this would be 5 minus 3x squared y squared dy dx's. And then bring everyone without a dx on the other side, and they're already here. So this is 2xy cubed plus 2. Then you would divide. You would find dy dx equals, well, 2xy cubed plus 2 all over 5 minus 3x squared y squared. Yes, it's not going to be as awful as you remember. Everything is easier in hindsight. Okay, you want me to blow your mind and show you how even much easier it could have been back then? Here's what I want you to notice. What is this top function here? Go back to the original. If you move this over to one side, x squared y cubed plus 2x minus 5y plus 7 equals minus 7 equals 0. What would I get if I took the partial with respect to x of this guy? I would get 2xy cubed plus 2, wouldn't I? Notice that what's on the numerator was, if I call this function here big F, what's on the numerator is the partial of big F with respect to x. What's in the denominator? If I go back to this original and I took the partial derivative with respect to y, I would actually get 3x squared y squared minus 5. Now the bottom is the opposite of that, so all I do is factor out a negative sign, and this is the partial of big X with respect to y. It turns out that your dy dx in the implicit differentiation case has a formula that goes along with it. And all those times when you were doing this algebra, regrouping terms, moving things to the other side, and you were killing yourself with the algebra, it turns out you could have thought of the entire process of implicit differentiation in terms of partial derivatives. And it's simply a matter of, if you want to find dy dx, differentiate the partial with respect to x, put it on top, partial with respect to y, put it on bottom, and then take a negative sign. You're going to learn that in 213. Pretend that you're surprised when your professor shows it to you, because he'll probably be hurt that you're all not as like flabbergasted. But yeah, so that's coming in 213 after you do the chain rule. You're just like, oh, wow, that's amazing, right? So from now on, try to act. But yeah, implicit differentiation, you can write it in terms of partial derivatives, and it's super easy. You don't need to go through all this trouble. I could have looked at the original and just grouped them, right? So if someone says something like, find dy dx if ln of x squared plus y cubed minus 2xy squared plus 7 equals pi. Now, of course, the Calc 1 student is going to have a nightmare and a heart attack at that, but you would actually know better. You would actually know that dy dx equals the negative. Go through and take the partial with respect to x. Divided by the partial with respect to y. Done. That's your answer. Do it in one shot, one liner, in your head. Meanwhile, all your friends are like taking 10 minutes to actually group all the terms and going through and doing all that stuff. Okay. All right. So that was our detour for today. Let's get back on track, because like I said, some people have to leave early. So now let's actually look at this again. Let's look at this guy. So here's what we're going to do. So z is a function of x and y. Z is our dependent variable, but I'm also thinking of the y as a constant here. And I mean, right now, even after like I showed you guys, it's sort of going to be, we could actually just use this formula to find it, but let's actually go through the motions. So what we'll do is we'll go through, and I'm going to find the partial derivative with respect to x of everybody. But my z is my dependent variable. So go through the first time, take the partial derivative with respect to x. Plus, now when I have x times z, I think of that as two functions, because my z is a function of x and y. So now I would do a product rule. Differentiate the x, leave the z, plus leave the x, differentiate the z. But differentiating the z, I need to add a dz dx. For the same reasons that I added the dy dx in the Calc 1 case. Then minus the derivative of 3z squared, well, that's going to be 6z dz dx, but partial z. Plus, now differentiate the x, I get yz, plus differentiate the z, I get xy dz dx equals 0. We did the product rule. For this term, we need the product rule. For the xz, we need product rule. And for this, we need product rule. And at this point now, you want to isolate this guy. So everyone with a dz dx, I leave them on one side. So that's the 2x, the minus 6z, the plus xy. Everyone else, I move to the other side. And that's where that negative in this general formula comes from that I told you guys, because you're bringing the negative of everyone to the other side. So here I would have minus 2xy, 2z, yz, take on all their negatives. And so now the partial of z with respect to x is going to be equal to minus 2xy plus 2z plus yz over 2x minus 6z plus xy. And again, you can notice that this is actually the minus of big F sub x over big F sub z. But that's really a spoiler for 213. So again, everything you did with derivatives in Calc 1, we can do it now again with partial derivatives. You just pay attention to one variable at a time. I think I skipped someone over here. Now we're here. You can use whatever I show you. Move things to the side until we're ready for it. Remember, we have both sections here. So for some of you, the test is Wednesday. For some of you, the test is Thursday. Let's look at this one. So again, we're going to be extending things now. Everything I showed you, of course, if we throw in more variables, I want you to be aware that if we throw in more variables, nothing really changes. So now let's look at a 3-variable function, f of x, y, z. Let's find the partial with respect to x, the partial with respect to y, the partial with respect to z. Okay, 3 volunteers, go. Who did I pick on? Haven't picked on Kevin for a while. Kevin, partial with respect to x. Okay, Ash is going to take y. I have a volunteer for. So just so the internet knows, Kevin's doing this. Ash is doing this. You is doing this. All right, go. Okay, so Kevin says it's e to the z times x e to the z plus 1 over yz. Okay, so let's actually see here. So we have x e to the z. We want to take the partial derivative with respect to x, which means e to the z is a constant, which means the derivative of that first term is just e to the z. Moving on, plus the derivative of ln of something is the derivative of the thing over the thing itself. So I put 1 over xyz, and on the top I put the derivative with respect to x of xyz, which is just yz. Now, of course, the yz's would cancel. And so this is just e to the z plus 1 over x. All right, so did Ash actually put down his guess for? So Ash just claims everything goes to 1 over y. So let's see. So of course, the first term is x e to the z. There are no y's in that, which means x e to the z is a constant as far as the y is concerned. So yeah, the first part is 0. Plus ln of something. To differentiate that, you put the derivative of the thing over the thing itself. So you put 1 over xyz, and on top of it, you put the derivative with respect to y of xyz. Well, that's just xz. The x's would cancel. So it's just 1 over y. And you, x e to the z, x is just a constant. So that the first term, the derivative is just x e to the z. You weren't going to say the same thing. I'm pretty sure that's totally original. Ask you if anyone ever did that with his name. No one has ever done that. Okay. So you guys are probably too young to even know who Soldier Boy is. Anyway, so all right, same thing. 1 over the thing inside the log multiplied by the derivative of the thing inside the log. So it's x e to the z plus 1 over z. Okay, all right. All right, so hopefully by now you guys are all getting used to this thing. Let's take it up a notch. Let's do higher order partial derivatives. So we can do second derivatives, third derivatives, all that good stuff. Of course, here things can actually be different. So when you talk about a second derivative, conceptually you're doing it kind of the same way, right? So it means you take a derivative and then you take a derivative again, okay? Now, however, because there are several variables, you can take the derivative with respect to any variable you want. Now, there will be times when a special order of partial derivatives are needed, but for now, let's just think of it as a general computational concept. So higher order derivatives means we take a derivative with respect to one thing, and then we take a derivative again. So for example, so that would be the second derivative. And if you take a derivative a third time, you get the third derivative, and so on and so forth. How does the notation work out? Let's do that first, because there's actually a very important thing to talk about notation. Higher order. Let's say I wanted to, I had take the partial derivative of some function with respect to x, and then I take the partial derivative with respect to x of that again. We write that as d squared f dx squared. It's actually very similar to the ordinary derivative notation for the Leibniz notation for the ordinary derivative, except here you have a curly d. You have a d squared because of the two d's on the top, and you have a dx squared because of the dx and the dx on the bottom. In the subscript notation, if I were doing the same thing, I say I take a partial derivative with respect to x first, and then I take a partial derivative with respect to x again. We would write that out as fxx. You do not write x squared. So you just write it as fxx, not fx squared. You write out the variable. Every time you take a derivative, you write out the variable. Okay, so now let's suppose I had the partial derivative of f with respect to x. Then I decided to take the partial derivative of that result with respect to y. This would, of course, the top would be d squared f, and on the bottom, I would have dy dx. Let's do it the other way. I have the partial derivative with respect to x. Now, of course, with the subscript notation, the subscript is down to the right. So the partial derivative with respect to y second, I would write it out here. And then we write it like this. Now, here's what I want you to notice about this notation. Here's something I want you to notice about the notation. The order is actually different. Notice that these two guys are in opposite order. And so this is why there's probably some cause for confusion here, but now it's not going to be, because I'm going to tell you how these are. See, in the Leibniz notation, every time you're taking a new derivative, you attach that derivative to the left. In the subscript notation, every time you take a new derivative, you attach that derivative to the right. So here, fxy, it's read left to right. This means x first, y second. On this part, though, when you have partial squared f, partial y, partial x, this is read right to left. Because the guy on the right was the guy that happened first. So this again says x first, y second. Okay, so the order will actually be the opposite between the two notations. So that's going to be very important. You're going to want to pay attention to that. Now, I did make a note of that here. Notice the difference in order. And let's actually just have you guys get some practice with the notation here. All right, so as I explained here, difference in order. All right, so I want you guys to tell me the subscript notation for this derivative here. So what we did, yeah, I saw your question, but because what I was saying is answering your question anyway, I didn't acknowledge it, but yeah. Here, I'm taking a third derivative. I want you to write these. Right, so the way to type out subscripts is you put an underscore. So like fx, you would write it as, if you wanted to type it, you'd write it as f underscore x. So that's how you would type it. Okay. All right, so write these guys out. Let's see, yxx, yes. Right? You literally go in the opposite direction, but you don't write squares, you write out all the x every time. So that's how you'd write this one down. right? So here, the y's occur on the right. Those are the guys that happen first. They would have to occur on the left in the subscript notation. Okay, so now we get it. All right, now another thing. You would have to now realize whenever we were in single variable calculus, we had f of x, y equals f of x, and I asked you, find the second derivative. We know you were finding f double prime, and the prime was fine because there was only one variable to keep track of. The notches just tell you how many times you're differentiating with respect to that variable. Now when we have f of x comma y, there are two variables. If I say to you, find the second derivative, the question now becomes, well, which one? I could find the second derivative by finding the derivative with respect to x first, then x second, or x first, then y second, or y first, then y second, or y first, x second, right? You now would have, for a two variable function, there are four guys that can operate as a second derivative. And when you go into the next class and you're finding maximums and minimums, remember the second derivative told us about concavity and all that good stuff, you're going to realize that you have to use all four second derivatives to talk about things like concavity and maximums and minimums. And doing a second derivative test is going to involve using a matrix with all the second order partial derivatives. So there are now multiple types of second derivatives. And then you can imagine how many third derivatives would there be? There would be a lot of them, right? So you can keep going. I think there are going to be about 9 of those guys. Now, let's actually find this. You'd rather not imagine? Okay. Don't worry, you'll worry about it next semester. Okay. So here is a two variable function. Find all possible partial derivatives. So when we say all second partials, this means fxx, fyy, fxy, fyx. So there are 4 that you'd have to find. Ash is already calling out fyy. Well, let's actually just go through these. What about fx? Someone tell me about that one. Just type it out quickly. Okay, so David had his guess. Let's see here. 3x squared, differentiate with respect to x, you get 6x minus 6x squared y plus 3y cubed. Right, and that is correct. So now, if you want to find f, so that means if you want to define fxx, that means you just take this thing that you already just differentiated and differentiate with x with respect to x again. That would give you, well, 6 minus 12xy. Now, if you wanted to find fxy, well, now you take this and you differentiate with respect to y. So that would give you minus 6x squared plus 9y squared. So those are 2 of your second order partial derivatives. Okay, so now to find the other 2, we'd first, of course, find partial with respect to y. That is going to give you minus 2x cubed, x cubed, plus 9xy squared minus 8y cubed. Right, which Ash had correct. Which means now I can find the partial with respect to y again. So then the first term would go to 0, the second term would go to 18xy minus 24y squared. And that's one of our second order partials. Then I can go in and find with respect to x second. And that would be minus 6x squared plus 9y squared. And the y term goes to 0. So we have that. Now let's make sure I'm not leaving anything off. All right. Now, hopefully that was clear how we did that. We're just taking the derivative twice, right? So we know how to take partial derivatives once. It seems like we're all catching on. So we're just doing it now twice. But now you have 4 guys that operate as a second derivative. So you have a lot more second order partials than in the first case, of course. Yes, Kevin noticed that fxy and fyx are the same. And it turns out that virtual Jhevon kind of knew that someone was going to notice that. So let's deal with that. Note that in the above, fxy and fxy are the same. Is this a coincidence? Well, yes and no, not really. There's a theorem about this, the mixed derivative theorem. It's usually called Clairol's theorem. The T is silent. It's another French mathematician. They always, it's always hard to pronounce their name. Basically, this is a theorem that says if you're, I think I missed some guys here. If f of x comma y and all its partial derivatives of the first and second order are continuous on an open region containing AB, then, so this is called Clairol's theorem or the mixed derivative theorem. It turns out that when you're doing multiple derivatives and you're taking partials in one order or another, it turns out that if you are continuous in the region that you're taking the derivatives, the order of partial derivatives does not matter, right? Now, again, that is if you are continuous in the region. It is possible for f sub xy and f sub yx to not be the same. However, there's a theorem that says if they're continuous, which in this case they were because we were dealing with a polynomial, those are continuous everywhere. They're continuous in entire 3 space. If they're continuous, the order of partial derivatives will always give you the same result, right? At any particular point, okay? So that is just something that you should know. It's called Clairol's theorem. And ordinarily, I would say you don't really have to know the name, just know the fact. But with the final that's coming up, they might ask you about the name of the theorem specifically as a multiple choice thing. What is this called when we can do this? Or, you never know. I don't know what to prepare you guys for exactly. But I think for the multiple choice or short answer final, actually knowing the names of things and knowing the statements of theorems specifically is going to be more important because they can actually nitpick at this stuff. That provides a lot of material for multiple choice questions, right? So they might say, is it true that fxy is always equal to fyx? The answer would be no, because that's only true if you're continuous in the region where you're taking the derivative. If you're not continuous, then all bets are off. They might be the same, they might not be the same, right? But if they are continuous, they're definitely the same. And that's why these guys, this and that were the same, right? It's not a coincidence, it's Clairol's theorem. If these guys were not continuous and these were the same, then yes, I would call that a coincidence. But because we have continuity here, it's not a coincidence. Now, this can actually, let's move this. We're almost at the end, guys. We're almost at the end. Like, this is the last round of examples right here. Everything down here, it's more conceptual speak. I'm just going to talk to you about some concepts, but we're not really going to do any examples on it. All right, these are the last real examples right here. These last 2. The last one. I'm so sad it's all going to be over. We're in the end game now. Raymond, raise your hand. Do you have a question? let's move on. Okay, so how can we use Clairol's theorem to make our lives easier? Every time you have a theorem, you might wonder, why would anyone even bother? Like, I mean, I guess it's cool, but why would you want to know this for sure? It turns out that applying Clairol's theorem can actually make your life a lot easier. For example, look at this guy. Look at this guy. Suppose we have z equals xy squared plus 2 to the y over arctan of y cubed. And I ask you to find the second order partial derivative with respect to y first, then with respect to x. Okay. Now, as long as your arctangent isn't 0, what you would do here is you would notice as long as y not equal to 0, which of course, I mean, that would make this thing undefined anyway. The functions here are continuous. This means Clairol's theorem applies. And I always spell this wrong. Oh, I think I got it. Oh, all right. Clairol's theorem applies. This means finding this dx dy, I kind of butchered that, would be equal to me doing this dy dx. And it turns out this one is easier. Right? So that's how Clairol's theorem can actually help us get away with things a lot easier. Notice that if I were to go in and try to differentiate this with respect to y first, I would have to actually differentiate the 2 to the y over the arctangent of y cubed, which I'm going to need to be applying the quotient rule with the chain rule because of the y cubed inside the arctangent denominator. Then I'd have to remember to how to differentiate 2 to the y. How do we differentiate 2 to the y? If I ask you the partial with respect to y of 2 to the y, right, it's 2 to the y ln2. Just checking that you guys actually remember that. How to differentiate an exponential if you ever had to do it. Right. But you see, I don't have to actually deal with that. Instead, I can just do the partial of z with respect to x. Now I can completely get rid of the second term because that is only a function purely of y's. And then I'd be left over with a y squared. And then I would get the partial of xy is just equal to 2y, which I know is equal to the partial of yx by Clairol's. So that is my answer here. So Clairol's theorem, it turns out that the order of partial derivatives does not matter when the function is, when the functions are continuous, or they're continuous on the region that you're taking derivatives of. So that's Clairol's theorem. One last parting example. So that's also something that might come that's something that might also be tested. They'll give you like several higher order derivatives to do. And it might be the case that the order in which they ask you to do it is not the most efficient order, computationally speaking. So while partial derivatives is easy for you guys, they'll probably make it a little bit tricky by doing this. No, they'll just ask you for an inefficient order. So you kind of waste your time and spin your wheels and probably make a mistake because the thing is so complicated by you differentiating with respect to one variable before another, right? So knowing Clairol's theorem and knowing that as long as the thing is continuous, the order in which you do it doesn't actually matter, you can get to the answer quicker, right? Can't you just take two partials, f sub xz equals f sub zx for this one? I'm not sure what you mean. I asked for f sub x partial with respect to x with respect to y, then respect to x. Oh, to this. All right, no, I was still rambling about the last example. Okay, let's do this one. All right, so we want to find f z z x. Someone tell me how to get there. You want to start with fx first? So that would be y e to the x plus ln of z. Then you would go fxz, that's just 1 over z. Then you go fxzz, it's minus 1 over z squared. Versus someone want, I mean, the functions here aren't so complicated, so I don't think it's going to be terribly inefficient either way. But let's say we followed this. Find the partial with respect to z first. This will give us that. Then find the partial with respect to z again. So give us that. Find the partial with respect to x now. And you just have the constant term. So either way, it wasn't bad here. But it's because you have like very easy functions. You didn't have something crazy like the 2 to the y over arctangent y cubed. But you'll notice you get the same answer. And again, we're just assuming that we're continuous, which means our z is positive here. So it can't be 0 because the ln wouldn't have worked. So dividing by z is not dividing by 0. So we're actually fine. xxz. Well, here, I think there's definitely some virtue in doing the z first. And that would just leave you with x over z. Then you do the partial with respect to x. Then you do the partial with respect to x again. Right. I think that's it. I mean, versus, let's just do the versus. If we wanted to do the partial with respect to x first, then I would get y e to the x plus ln of z do the partial with respect to x second, I would get, well, y e to the x, then do the partial with respect to z, then I would get 0. Right? You'll get the same answer either way because we have continuity here. All right. So that is partial derivatives, right? Geometrically, we're just slicing through our surface and finding the slope of the tangent line in one direction at a time. Computationally, what this means is whoever you're taking a derivative with respect to, pretend all other variables are constants. You write a squiggly d to denote the fact that you're doing this. We can do everything we could have done with first order derivatives, including things like implicit differentiation, quotient rule, property rule, chain rule, all that good stuff. In fact, from this, we can get a shortcut for doing implicit differentiation, which you're going to talk more about in 213. They'll probably derive that based on the chain rule. There is a multivariable chain rule. And we can, of course, take higher derivatives, but there is something that you should pay attention to. The order matters between the two different notations. They're actually read in opposite orders. However, there's a nice thing called Clairol's theorem, which tells us that the order actually does not matter as long as we're continuous where we want to differentiate. If we have continuity problems where we want to differentiate, then you kind of have to stick to the order that you're supposed to go in and be careful. And knowing that the order does not matter can actually cut down our work considerably in certain situations. Yeah, so that's it. Now, I just want to have a little bit of discussion about differentiability. So differentiability, this is our ability to actually take the derivative of something. Now, we know about a lot of things, and I'm not really going to go through any specific example here, but just to call your attention to some things that we knew about differentiability from Calculus 1. So for example, we knew things like, well, if a function is differentiable at a point, then it is continuous at that point and all that good stuff. And so we might ask ourselves, all these things I know about differentiability and continuity back from Calc 1, which of those things are actually true when we talk about differentiability in terms of partial derivatives? It turns out when we talk about the total derivative, total differentiability, he has a lot of similar properties like the derivative in Calc 1. Like, yes, if a function is differentiable, quote unquote, at a certain point, then it automatically means it is continuous at that point. It will also mean that you can find the equation of a tangent plane to that point, to the function at that point, which approximates the plane. Similar to how you could find a tangent line that approximates a function. That has all these continuity consequences and it still works. However, the same cannot be said for partial derivatives, meaning there are examples out there where you can find partial derivatives at a point of a function and the function isn't even continuous at that point, which is very strange to think about. But here's a specific example, right? This function, it's not continuous at 0, 0. We actually showed that. That was our example of something that does not exist in the last section. However, it turns out at 0, you can actually compute both partial derivatives and they'll actually be continuous. They'll actually be 0 at the origin. Even though the function itself does not exist at the origin. It's not continuous there. So there are some sort of strange things that can happen with differentiability. And even though we don't know what the derivative actually looks like yet, we can know when it will or will not exist. And we kind of take our cues from single variable calculus. Another way of knowing that the derivative would exist, even if we don't go through the limit definition, is to just pretty much use that formula that we got from the linear approximation formula. If the change in y can be expressed as this sort of equation where epsilon approaches 0 as delta x approaches 0, we know that it's differentiable there. In a similar way, in the multivariable case, if my change in z can be approximated or set to be this equation, I can approximate it using 2 of the partial derivatives at a time. then we say it's differentiable at that point, meaning we can find something that performs all the functions of a derivative. Now, of course, in higher dimensions, this thing is going to be a vector or a matrix with a very special formula attached to it. But knowing that that thing exists, we can use this criterion right here. And again, you might see a few problems like this in your homework, but I don't anticipate anyone actually asking you to show that something is differentiable by doing this. But again, it provides a lot of ammunition for like a multiple choice thing. They can actually ask you about this sort of thing. So I just want to put it in here so that you guys can read it, commit the things in boxes to memories, and go on. Now, it turns out, however, if you can show that all your partial derivatives are continuous throughout an open region, then it's also differentiable at that region. So having the partial derivative exist at a point does not necessarily mean that the function is continuous at that point, or the function is actually differentiable at that point. But having all partial derivatives continuous at all points in an open region will mean that the function is differentiable in that open region, and the function is continuous in that open region. So again, the partial derivatives don't always tell the whole story, and that's just a cautionary tale, really. They're very cool, they're very useful, but knowing about one partial derivative or the partial derivative at certain points is not good enough to talk about differentiability in general. You need a lot more requirements there. And so that's what this is about. And here's a particular function which you guys can work through. But yeah, that's basically it. And that's kind of it. That's what we want to talk about. That's the course, guys. That's Math 212. We covered everything. In fact, we covered more than everything. So you guys will actually know a little bit more than the other guys. And but remember, in the next class, try to act surprised sometimes when your professor is talking about certain things. And yeah, that's kind of it. Partial derivatives, that's the last topic. So hopefully that's fine. What I want to do with you guys now, I want to actually do an exercise. I would like you guys to now go and log into your Blackboards, because we're going to do an experiment. So in terms of lecture material, we're done, but this is something very important. I want you guys to make sure that you can do this. Everybody say we're at a checkpoint. Yeah, that's true. The final boss is coming on May 21st at 3:30. But go and log into your Blackboards. Give you guys a couple minutes to do that. As always, I'll post the video and the notes here on YouTube when we're done. But let's see here. Boom. Let's hope this thing then logs up. Can you guys see my browser? All right, cool. Let's just go into, oh God, whatever class I go into now, it's gonna be like, well, do you prefer this class to our class? Like, why do you go into the GH section? You know what, I'm gonna go into the other section. No favorites. So this is another class that I'm actually filling in for because the professor couldn't continue. So here is what you guys should be looking for. Click into your class. So if you're in the GH, click 212 GH. If you're in RS2, click 212 RH2. In the green menu bar, at the bottom, you should see a link that says sample test. Does everyone see it? No, he's just ill. I'm filling in for it ill because he's ill. He's a good guy. He's a good professor. He's a veteran. He's been around longer than I have. But you don't see the class. You don't see 212 GH anywhere? Oh, you don't see the test, but you can get into the class? This is strange. Let me see. All right, hold on for a second. Let me see what's going on here. Let's see what is going on here. I mean, okay, so section GH, refresh your browsers and let me know if you see it. All right, and now section RS2, refresh your browsers and let me know if you see it. Okay, good. All right. So click into that, click on it. You'll see this, you'll see a sample exam there. Okay. So now what I would like you guys to do is you're going to take the sample exam. This is what your final is going to look like. You're going to click it. There's going to be, I'll have a link that appears here on the day of the final. It'll be in this green section somewhere. I'm assuming that it is, yeah, no, this is just a sample. It's not a real test. You're not getting 4 multiple choices. Okay. And it's not going to last 10 minutes. They say this lasts 10 minutes, but I want you guys to take like 3. Okay, because you can answer all these questions. It doesn't have to do with 212. It's just some general math questions just for you to see what it's like. So you'll go into the final, you'll see instructions here, and you'll enter the final exam through this link here. Now, once you enter that, you'll see the instructions again. So you should read these instructions and familiarize yourself with it because the final exam will have similar instructions. One thing I want you to notice is that where did they say here? Yes, you will not be allowed to go back to a previous question or look ahead to remaining questions. So you're doing this exam like you're doing partial dirties. You're focusing on one thing at a time. You go to question 1. You would finish question 1 before you can move on to question 2. Once you go on to question 2, you can't look back at question 1. You also can't look ahead at question 3 or anything. You are doing one question at a time. You need to move on as time is going on, right? So you have to just keep going. So there will be a suggested time limit within the questions. And when you do the test, you're going to see this, but that's how it's going to go. You're going to enter the final, you're going to see the instructions, then you're going to do one question at a time, and you just move on one question at a time. Do not spend too much time on any one question. Do not exceed the recommended time limit, because then that means you might run out of time at the end. So that is a thing that's going to you'd need to be aware of. That's how it's going to feel. But the test, it's going to have more questions than this. I don't know for sure how many questions. I'll try to find out. But I do know it will be the full 2 hours and 15 minutes, right? You'll be given that much time. So now what I'd like you guys to do is I'd actually like you to enter this exam and do the exam. I will give you guys 3 minutes to get through 4 problems, and then we'll continue after. We'll do a follow-up at the end. Go. No, you're not scanning anything for the final. It's completely online. It's going to be graded by the test online. As far as I know, you don't have to show your work. But anyway, go, finish this up. 3 minutes. All the other classes can take 10 minutes. They don't know who we be. So to find the test, you click on sample exam, you scroll down to the bottom, and there's a begin in the bottom right corner after you read the instructions. All right, so hopefully we're all done. You guys got through that okay? All right, so what you would have seen is you click begin. You get in, you'll see the instructions again, it'll be on every page. You go down, you'll notice here in the parenthetical statement, there's a suggestion. Oh, you should be taking no more than 2 minutes on this, okay? For the function, find the derivative. It should be 2 times that times that. That's this one, it looks like. Huh? You're testing me? Me? Okay, let's go down. So you'll notice that you can't move forward or backwards. You just have all of these. This is the gamma function, but you don't even really need to know what that looks like. But notice that it's defined in terms of factorial. So I think just multiplying by an n would get you the other one. Then you scroll down. What's the derivative of x? The integral of x. Oh my God, that's a tough one. Well, at least we can't forget the plus c, right? So you'll go in and it's just like this. You'll click on one thing at a time. Can't move forwards or backwards. So it looks like the top one is the one. And then you save and submit. You'll get a warning. Then it's like, okay, blah, blah, blah. You finished in 1 out of 10 minutes. And then if you click OK, it actually tells you how you did. And somehow we got 4 out of 4 points on this. But yeah, the file's going to be like this, except it's going to be 212 material and it's going to be 2 hours and 15 minutes long. But that's what it's going to feel like. So on the day of the final, you're supposed to log into your Blackboard. You will see the test appear in this situation right here. And yeah, you're going to go through the test. You won't be able to move forwards or backwards. And there will be a suggested time limit for each question. And yeah, you just keep going. And that's what it's going to be like. So I wanted to make sure that everyone could go in and actually try it and there was no issues. But it seems like most of you can do it. For those of you who could not make this lecture and you're watching this on YouTube, make sure you can log into this and do the test. I'll leave this guy open until, I think how long did I leave this open? I forgot. Until 5:15. Right, so you have until 5:15 to make sure you can get in and you can take this test. So yeah, so next week you have your test. I'm not done grading test 1, by the way, so I think someone asked about that earlier. And I finished writing the mock for test 2, but I didn't upload it online. I'll do it as soon as we log off here. So you should see that in a little bit. I have to upload it to Top Hat, but I have to manually do it for each question. So it's kind of annoying. So yes, our next test is on Top Hat, but our final is on Blackboard. So Top Hat is our in-class protocol, but I set that up before the math department made up its mind that we were doing Blackboard. So we're going to continue with the Top Hat because I like that way of doing it anyway. I like it a lot better. So next test is on Top Hat. So I'll upload the mock test to Top Hat. I'll do it a little bit after I log off. So you can start practicing for that test, but it just covers the second half of the course. It's also going to be an hour-and-a-half long. And yeah, that's kind of it. We're kind of done. We're going to wrap up. So I think that's it, guys. So on Monday and Tuesday next week, we will be doing a review. We can go over questions that you have from the second mock test, I guess, or we can just start reviewing anything in general that you might want to talk about. But that's kind of it. Also, if you guys want, we could potentially have like an extra class on the Friday of next week, just to kind of review everything about the final. Maybe I can check in and give you guys any extra information that I can find out by that point. But that's it, partial derivatives. Last thing you have to know, let's actually, let's finish the semester off strong. So we are going to stop there. So bye, everybody. Enjoy your Friday. Take care. Yeah, so I think there's like different classes are having, they're trying to do a uniform grading scheme. And so different sections are doing different things. I believe, and I can verify this, that for the 212, they're pushing it to make the final be worth 65% instead of the usual 40. So I'll give you guys more information on that also next week, see how we're going to do that. Anyway, I know it's not, sir. But that's where we're leaning, and I'd have very little choice in that as far as it seems. Anyway, we'll stop there. I'll see you guys next week. No, don't worry. Whatever they throw at us, we can handle it. All right. Ciao.